Welcome you all for the GATE training session on subject design of steel structures. Myself Rajit TJ, Assistant Professor, Department of Civil Engineering, Vidyavardha College of Engineering, Mysore. So if you see the GATE previous question paper analysis, from steel structures, we will going to get minimum 2 mark. So if you observe in the last year, 2022, so they asked one question in the morning session, one question in the afternoon session of weightage 2 mark. So maximum we will going to get. So this is what the previous year analysis. Maximum we will going to get 2 to 3 marks from steel structures. So when come to the syllabus, we have working stress method, limited design concepts, design of tension compression members, beams, beam column, column bases. With respect to connections, they included simple and eccentric connection, beam column connections, plate girder, trusses, concept of plastic analysis, beams and frames in case of plastic analysis. So here we need to concentrate on the basics of working stress and limit state method and some basic design concepts of tension and compression members and beams, and mainly we should study the connection part, simple and eccentric connection. If you observe the previous year question papers, they're frequently asking questions on this. And also here no need to read this plate guard and trusses, so you can go for just basics thing. So here one more important concept here is the plastic analysis on beams and frames. So you're going to see the questions on this topic, plastic analysis. So this is about syllabus. So when come to the properties of steel, the unit mass of steel is 7850 kg per meter cube. Modulus of elasticity 2.010 per 5 Newton per millimeter square. So these things you should know because sometimes they will ask directly 1 mark question for this. The Poisson ratio of steel is 0.3, rigidity modulus 0.769 10 power 5 Newton per millimeter square. Quotient of thermal expansion for steel is 12 into 10 power minus 6 per degree centigrade. So when we go for loads and forces, we need to consider for the design of steel structures. So first we need to consider the dead loads. So this available in Indian Standard Code IS 875 Part 1. Next, imposed loads are live loads, with the details available in IS 875 Part 2. Wind loads IS 875 Part 3. Earthquake loads IS 1893 Part 1. Erection loads class 3.3 of IS 800. Accidental loads which are going to occur during erection of the steel structures, we need to take the according to class 5.3.2.2 of IS 800 2007, the latest version of the code, and notional loads according to class 4.3.6, which are the extra loads we need to consider, particularly in case of steel structures, not in case of RC structures. So secondary effects, we need to go for class 3.5.7 of IS 800. So these are the loads we need to consider for design of steel structures. When come to the load combinations, this is an important one. So what are the, in the last slide we know what are the loads coming onto the steel structures, particularly in case of steel structures we need to look into the erection load. Anyway, if you go for the load combinations, so which is available in class 3.5 of IS 800, the first combination is dead load plus imposed load plus crane load. So the crane load will come only in case of steel structures. So whereas in case of RCC, we're supposed to consider only dead load and imposed load. Here we need to add one extra thing, that is crane load. So crane load will come across due to the erection of steel structural elements. Next combination, dead load plus imposed load plus crane load plus wind or earthquake load. Here the one more load we need to consider in this combination is wind or earthquake. So since the wind and earthquake both are not simultaneously will going to occur, therefore while considering the load combination, we can take the highest one, that is wind or earthquake load, in addition to crane, imposed and dead loads. So for third combination here is dead load plus wind load or earthquake load, and fourth combination here is the dead load plus erection load. So the fourth combination is exclusively for steel structures. So these are the load combinations according to class 3.5. When go for the limit state design methods, so the concept here is we need to satisfy this condition. Design actions is nothing but design loads must be less than or equal to design resistance of the structure. So during its lifetime, the structure has to have the more strength when compared to the load acting on the structure. So according to the limit state method, we can categorize the limit state into two categories: the limit state of strength and limit state of serviceability. Limit state of strength deals with strength properties, whereas limit state of serviceability deals with the properties of the structure during its service, during its usage. So these are all the points we need to remember. So sometimes they will ask 1 mark question directly. So the points will come under the limit state of strength and also limit state of serviceability according to class 5.2.2 of IS 800 2007. The limit state of strength includes loss of equilibrium of the structure or as a whole or any part of the component. So that is the first limit state according to limit state of strength. So loss of stability of the structure including effect of sway and any part of the supports or the foundations. And the third limit state is failure by excessive deformation or the rupture of the structure or any of its parts or components. And fourth one is fracture due to fatigue, and the fifth one is brittle fracture. So these will come under limit state of strength. Whereas if you go for limit state of serviceability, we need to look into it while during the service of the structure. The first one here is the deformation and deflections, and the second one is vibration due in the structure due to the loads and causing discomfort to the people who are using that structure. And the next is repairable damage or crack due to fatigue, that will also come under limit state of serviceability. Corrosion and durability, and also the fire. So fire will come under limit state of serviceability, whereas in case of strength, loss of equilibrium, stability, so failure, fracture damage, and brittle failure will come under limit state of strength. We should remember this. So sometimes they will ask 1 mark question directly. So next is design actions. Design action is nothing but design loads. So just now we discussed about the load combinations. So for the load combinations, we should multiply the load factors. Okay, those factors here we need to take according to table number 4, that is class 3.5.1 and 5.3.3 of IS 800. Those factors we call it as partial safety factor for loads, gamma F for limit states. So this is available in steel code book. The design action includes what? The load or the characteristic load we need to multiply with partial safety factor. So to get design load, where QCK is the characteristic load. So after calculation of the load combination, we will end up with the major load or the critical load. For that load, for safety, we need to multiply with partial safety factor, which are available in table number 4 of IS 800. Here, if you observe here, this is the first load combination. If you go for first load combination, dead load plus live load or imposed load plus crane load. Here we should multiply 1.5 for the dead load component as a partial safety factor with respect to limit state of strength, and 1.5 for the live load component for leading and also accompanying, but prefer we will go for 1.5. And also for wind and earthquake, here we not consider. Okay. So similarly, in case of limit state of serviceability, we need to take dead load as 1.0 and live load as 1.0. So these are all the partial safety factors we should consider while calculating what? The design load or the factored load. So these values also we should remember. Here we can observe the other load combinations also. Dead load, live load, crane load, plus wind load, earthquake load. So what we discussed in the earlier slide. So this is what the partial safety factor for loads. When go for design strength of the material, the design strength of the material we should take as lesser than that of strength of the material. So what we studied in the materials laboratory. So if assume that if the strength is SU, we need to divide by gamma M. Gamma M is the partial safety factor which will take care about the uncertainties while manufacturing the material. So that's why we're going to decrease the quality of the material by using partial safety factor for material, that is gamma M. Whereas in case of previous one, so the partial safety factor for loads, it will take care about uncertainties will occur during the assessing the load combinations of the loads. Okay. So now if you go for gamma M, partial safety factor for materials according to class 5.4.1 of IS 800 2007. So according to table number 5, so they given different types of partial safety factor for materials. So if you observe by one, so first one is when the material is yielding by governed by yielding. When the metal is failure by yielding of all fibers, then we should take the value as 1.10. If the member is failed due to buckling, then we should take the gamma m naught as 1.10. If the member is governed by ultimate stress, then we should take it as the gamma m1 as 1.25. With respect to connections, we all know that steel structures depends on the mainly on connections. If you go for bolts, again they have the shop and field fabrication. For bolts, for bolt friction type and bearing type bolts, that is gamma mf and gamma mb, we should take always as 1.25. We can remember this. Whereas in case of rivets also, we should take it as for shop or the field is nothing but when at site. A shop is nothing but during workshop, some of the researchers will go into manufacture in the workshop where we have good degree of quality control. Therefore, that's why the partial safety factor is less when compared to field fabrication or site fabrications. Inside we don't have much quality control. Okay, so if you go for welding, so in case of shop fabrications, we should take 1.25. If you go for field fabrication, we should take higher value, that is 1.50, since we have less quality control at field. So this is what the partial safety factor for materials and partial safety factor for loads. So next, if you go for one more criteria, that is major criteria is deflection according to class 5.6.1. So here they given in table number 6 of IS 800, they given deflection limits for different types of steel structures. So based on the vertical and lateral deflection, and also the based on the design load what we are considering. So based on different members like gantry girder, beams, and also the columns, frames. So and also based on the support condition, we can go for the maximum deflection criteria according to the code. So here we need to remember for gantry and gantry girder, we need to remember these values: span by 500, span by 750, span by 1000. Sometimes they will ask 1 mark direct question here. And also for live load, for a simple span building, so we should take it as span by 300 if it's a brittle cladding. If it is a elastic cladding, we can go for span by 250. So these values you should remember, that is maximum deflection or the allowable deflection according to IS 800 2007. So if you go for some of the previous asked question, previous question questions. So first question is, which of the following is not a limited design state of strength? We just now we discussed the component which are coming under limit state of strength. That is, fracture will come under limit state of strength, brittle will come under limit state of strength, rupture. Whereas the vibration will come under limit state of serviceability, not in limit state of strength. This is what 1 mark question. So based on the different criteria of limit state of strength and limit state of serviceability. If you go for next question, the partial safety factor, this is what the gamma m for materials. Since it is materials, we should take it as gamma m according to table number 5. So governed by buckling is, if it is buckling, we should take it as 1.10. If it is governed by yielding also, we should take it as 1.10. If it is governed by if it is governed by the ultimate value, then we should take it as 1.25. The question is based on the partial safety factor for materials according to IS 800. So if you go for the one more question, so this is on load combinations. For combination of dead load and earthquake load, the partial safety factor as per the limit state method is, just now we discussed here in the previous slide. So this is what limit state of strength, limit state of serviceability. Here we need to take these values based on the dead load live load combination. Here in this question, they are asking for limit state of strength and serviceability for dead load and also earthquake load. Here the value here is 1.2 and 1.2 for dead load and earthquake load respectively. That is partial safety factor for loads. So this is according to the code table number which is available in table number. The load combination value is available in table number 4. That is partial safety factor for loads available in table number 4. For material is available in table number 5. So when come to next important aspects of steel structures, the important concept, the design of connections. So in case of steel, we have two types of connections. One type is a bolted connection. One more important type is a welded connection. So in exam, If I observe, if you observe the last question papers, you're going to see many questions on the connection part. So that's why we should study both bolted and welded connections. Okay, if you go for bolted connections, first you should know what are the components of the bolts. Here is the components of the bolt. This portion we call it as shank portion, head portion. This entire portion we call it as shank portion without thread. So this thread portion we call it as thread portion of the bolt. This is called ordinary bolt. This is what the nut and also the washer. Here this side we can able to see the high strength friction grip bolt, where we have here the force will going to transfer through the bolts through both friction and also the bearing. So here the load will go to transfer through shear. So in case of ordinary bolts, so these are different types of bolts which are using for connection of steel structures. If you go for the properties of the fasteners, nothing but bolts. If you assume that if the according to this IS 1367 1991, if the grade is 4.6, so preferably we're going to mention for always the for the bolts the grade of bolts. So we're going to mention like this. If you observe 4.6, 4.8, 5.6, 5.8, 8.8 and 10.9. Now the question is what is 4 and what is 6? Okay, this is what the grade. So here 4 indicates the ultimate stress tensile strength of the material. For example, if you consider the 4.6 grade bolt, then the tensile strength of the bolt as a steel material is 400, whereas the yield strength of the bolt will be 240. How we get 240 here? 400 into 0.6. So this is 0.6 indicates the fraction of the yield stress. How we going to get that? The ultimate stress divided by this, multiply with 0.6, we're going to get the yield stress. Or the 0.6 indicates that yield stress by the 400, the ultimate stress. So here if you observe, if you take a property class 4.6 bolt, the number starting number 4 indicates the 1 by 100th of the nominal ultimate strength of the material. For example, if it is ultimate strength is 400, if you divide by 100, you will going to get 4. That is what your first letter. So then the number 6 indicates the ratio of yield stress to the ultimate stress. Assume that your yield stress is 240, then divided by 400, you're going to get the value as 0.6. So this is how we're going to get the different types of bolts. It will start with 4.6. Based on the strength, it will going to increase. So compared to 4.6 and 4.8, 4.8 grade bolts are having more strength when compared to 4.6. So this value will going to use for the calculation of stresses or the strength of a bolt in the problems, numerical problems. So next, if you go for different types of bolted joints, here I have shown 4 category of bolted joints. So assume that this is plate number 1. So this is plate number 2. I have placed it plate number, plate number 1 below, whereas plate number 2 above 1. So then I have connected through 3 bolts. So this joint we call it as lap joint. If you keep one plate above the other, those joints we call it as lap joint. If you keep the plates here, if you go for this joint, this plate number 1, plate number 2, if you keep one adjacent to other, then we call it as the butt joint. So if you go for lap joint, this connection we call it a single bolted lap joint. Here I used one single row of bolts. From here to here, there are 3 numbers, 1, 2, and 3. So these bolts are used here. Okay, this is what one view. This is one more view, the cross-sectional view. If you go for cross-sectional, this is what your plate number 1, this is what your plate number 2. We have kept plate number 2 above plate number 1 and we are connected using the bolts. So this, since you are connected only single rows of bolt, then this connection we call it as single bolted lap joint. If you go for this problem, here I used 2 rows of bolts. Okay, 2 rows of bolts. Therefore, this joint we call it as double bolted lap joint. So lap joint means we should keep one above other, the bottom and the top plate, one above other. If you connect using 2 rows of bolts, then we call it as double bolted lap joint. Okay, when compared to single bolted, double bolted lap joint will going to transfer more, load. It will going to carry more load when compared to single bolted lap joint. So when come to other types of joints, that take butt joint, when you keep one plate adjacent to other, So this is the to when you keep like this, we need to place one cover plate above and one cover plate below. If it is placed only one cover plate, then that connection we correct as single cover, single bolted but shunt. Okay. If you go with double cover like this, so top cover plate and also the bottom cover plate, then we correct as double cover, double bolted. Double bolted means if you consider this, edge from here, this is the point where two plates are meeting. Since we kept one adjacent to other, if you use two rows of bolts here, if you use two rows of bolts, then we correct as double bolted joint. If you use only one rows of bolt on one side of the this joint, okay, then we correct as single bolted joint. So if you keep one adjacent to other, we correct as butt joint. So when you keep one plate above other, then we correct as lap joint. So this is what the typical bolted joints. So here out of these four, single bolted, double bolted, lap joint, single cover, single bolted butt joint, double cover, double bolted butt joint. Okay, the double cover, double bolted butt joint is the strongest one, since we are connected with more number of bolts. And here the main, if you observe the eccentricity, the thing is the from force from here it has to transfer to this side, correct, through these bolts. So when you apply force on this, since there is no eccentricity between these two lines, that is line of action of the forces, this will going to carry more load when compared to other. Because if you go for, if you apply for the, if you consider the single bolt or single cover, if you apply force on this, it will going to transfer to this bolt, again it will transfer to the cover plate, again this bolt, again it will transfer to again main plate. Okay, so since we are connecting the main plate, here we're going to get some eccentricity. Okay, here also there will be some eccentricity. Here the top force is like this, the bottom force will be like this. Here also we're going to get some eccentricity. Here also we have the eccentricity. Okay, out of these four joints, the only one joint will not get eccentricity here is double cover, double bolted butt joint. That's why that joint we correct as strongest joint compared to other joints. Okay, when come to the different types of modes of failure of bolted joints, so the thing here is in problems we need to calculate the strength of a bolts. So to know the strength of the bolt, we should know the different types of failures or different types of strengths of bolted joints. So the bolts joint, this is what the bolted joint here. So this one and also this also bolted joint. These are failure joints. So because of application of the load, the joint has already failed. Okay. So the joint will going to fail in different modes, particularly the bolted joints. First one is shear failure, bearing failure, tension failure, three kinds of failures, and also next bearing failure, tension failure of plates, and the last one is black shear failure. So these are the typical failures of the bolted joints. If you consider first one, here what will happen? The bolts what were used for the connection, because of heavier load acting on the bolts may be fail due to shear. That means if this is the bolt, okay, so if this is what the plate, because of this force, the bolts will go on to break into two pieces like this. So if it is a single if it is single bolted lap joint, okay, that type of failure we call it as shear failure. It is bearing failure means when the bolts having the strength, bearing strength is lesser than the plate, then there will be a bearing failure of bolts, and there will be a tension failure of bolts when the bolts will break into in the different types of pieces, number of pieces based on the double cover, the double shear or single shear concept. Here, if you observe this figure, this is what the bearing failure of plates, not the bolt. The bolt is stable here, the bolt is stronger one, whereas this failed due to the bearing failure of plate. That's why they given different two types of failure for plates, that is bearing failure and also tension failure. So this is an example for this first figure is an example for what the bearing failure of plate. So here the bolts are strong but the plate is weak. If you go for last one, here in the black shear failure, what will happen? The entire joint will going to break into two pieces. Here, if you observe, this is the joint, the bolts are in intact place, but the joint is broken into two pieces. This is block number 1, this is block number 2. So this is what the different types of failure. Whenever they ask it for joint strength, okay, giant strength of a bolted joint, we should calculate all these 5 strengths. So the shear strength of the bolts, the bearing strength of the bolts, tensile strength of the bolts, bearing strength of the plate, tensile strength of the plate, and also black shear failure. Typically, what we'll do out of these things, so we can avoid this tension failure of plates and also bearing failure of plates, okay, and also the tension failure of bolts by providing proper end and edge distance. I'm going to discuss in the next slide what do you mean by end and edge distance, okay. So typically we're going to consider shear, bearing, and also the black shear failure. Out of three, whichever is least, that one we should consider for the design of bolted joints. Okay, this is about the failure of bolted joints, nothing but the strength of the bolted joints. So if you go for the location of the bolts or the fastened according to class 10.2, okay, the clearance bolts for the fasteners we should take like this according to the table number 9 of IS 800. Okay, here for a diameter of bolts between 12 to 14, then we should take the standard clearance as 1 mm, the overside clearance as 3 mm. Okay, this is what the extra hole we need to make to put our bolts in case of plates. So assume that this is what the plate, here we need to put one bolt, then how much hole we need to make based on the diameter. If the diameter of the bolt is 12 to 14, then we should add 1 mm. If the diameter is 16 to 12, 22, then you need to give the clearance here. Clearance to insert the bolt easily and to tight easily, we should give this clearance. Okay. So size of the hole or the bolt hole, how much we should make here is the nominal diameter of the bolt or the fastener plus clearance. So this depends on the diameter of the bolts. Okay. If you go for the specifications of bolted joints, we all know that the pitch and edge distance. What do you mean by pitch? Pitch is the distance between two consecutive bolts. Okay. If you consider this as pitch, 1 second. If you consider this connection, this is what the plate, this is what the two bolts. The distance between these two bolts, according to the code, the minimum distance how much we should provide here is why? Because the strength of the joint depends on these criteria, that is the distance between the bolts are parallel to the direction of the load, okay, and perpendicular direction of the load. So we need to decide the edge distance and also end distance and also the pitch between the bolts, nothing but the distance between the two consecutive bolts. So if this is the load direction, if you measure the distance between two consecutive bolts, that distance we correct as pitch. So according to the code, the minimum spacing or the minimum distance we should provide here is 2.5 times of the nominal diameter of the fastener. So the minimum value should not be less than. That is, we should provide minimum of 2.5 times of the diameter of the fastener. Assume that your diameter is 20, then we should provide 20 into 2.5, 50 mm we should give the gap here. So this is what the distance between the two bolts parallel to the direction of load. So then what will be the maximum spacing, how much we can give here? So this maximum spacing depends on the different criteria. So the value should not be exceed 32 times of the thickness of the thinner plate or 300 mm, whichever is less. It should not exceed 16 times or 200, whichever is less for tension member, and shall not exceed 12 times of T or 200 mm, whichever is less for compression member. So this maximum spacing depends on whether you are using for compression member the connection, whether you're using for compression tension member, or whether you're using for other type of connection. Okay, where T is the thickness of the thinner plate, where pitch, why we need to provide 2.5 times here is to tight, while tightening the bolt, we should not come across the other bolt, adjacent bolt, to disturb the process of tightening all those things. That's why we're going to provide 2.5 times. And to avoid stress concentration between the bolts also, we should provide minimum of a gap of 2.5 times of the diameter. So if you go for the maximum, minimum and maximum edge distance is nothing but if you take this as a bolted connection. So this distance we correct as E, that is end distance. This we correct as edge distance. So this distance between the bolts from center of bolts to the edge of the material plate, then we correct as edge distance. So from center of the bolt to the The end of the connection we correct as end distance. So these two we should provide properly to avoid the failure of plates due to excess of load. We should provide properly this, the minimum and maximum edge distances. The value shall not be less than, according to the code, shall not be less than 1.5 times of the that whole diameter. Okay, in case of and flame cut edges, the value must be shall not be less than 1.5 times in case of rolled or machine cut edge. So nowadays there we are all going for machine cut edge. We need to provide minimum this distance, edge and end distance should be minimum of 1.5 times of the whole diameter. How are you going to get whole diameter? So from table number 19, we should take the clearance plus diameter of the board. We're going to get the whole diameter. Whole diameter 1.7 for and flame cut edges. Whole diameter into 1.5 for flame cut edges. So the bolts which are connecting for tacking purpose, we should provide a minimum edge distances 32 times of the thickness of the thinner plate or 300 whichever is less. The maximum edge distance we can provide here is 12 times of thickness into epsilon, where epsilon is the square root of Fy by 250. So preferably if you go for a 250 grade yield strength steel, then epsilon will be 1. So 12 times of T, where T is the thickness of the outer plate. This is for maximum edge distance. This also according to code. So to give the maximum efficient joint, we should follow these values, that is minimum and maximum pitches and also minimum and maximum edge and end distances. So next thing is, just now we discussed different types of failure of bolted connections. Okay, in bolted connections we need to study the shear shear strength of the bolt, bearing strength of the bolt, and also black shear strength. If you go individually the bolted joint, okay, we should calculate the shear strength of the bolt individually according to the code, and we should calculate the bearing capacity of the bolt. Okay, if you go for shear capacity of the bolt according to class 10.3.3 of IS 800, this was the formula. So the design shear strength of the bolt is equal to VDSP as governed by shear strength, a VDSP equal to VNSP by gamma MB. So we know already what is gamma MB. Gamma MB is the partial safety factor for material which is available in table number 5. Okay. So what is VNSP? VNSP is the nominal shear capacity of the bolt. So how we are going to calculate this? So using this formula, so nominal shear capacity of the bolt equal to area into stress. This formula is also available in IS 800. Fu by root 3 is the stress into area. What is this area? NN ANB plus NS ASP. What is NN or ANB? So here n small n stands for the net area. Net area means where we're going to take, assume that if you take the bolt, we already know if you take ordinary bolt, this is the head portion. Okay. So here we're going to have shank portion and also the thread portion. So assume that whenever you're using these bolts to connect, two plates, okay, here like this, if the thread portion, if the thread portion falls in shear plane, so this is the plane where the bolts will going to fail when you connect two number of bolts, 1 and 2, okay. If the thread portion falls in shear plane, then we should consider NN value. The NS becomes 0. Assume that if the shank portion falls in this plane is nothing but the failure plane, then we should take this value, NS into ASP. Okay. If in case of double shear case, double shear means there will be double failure surfaces. So for bottom, sometimes you may get thread portion, for top sometimes you may get shank portion. Then we should take both NN and AS. Based on number of shear planes, we should decide NN value and NS value. Assume that if the thread falls in shear plane, if the thread portion falls in shear plane, then NN becomes 1 in case of single shear failure. In case of double shear failure, NN becomes 2. In case of shank falls in shear plane, in case of single shear, NS becomes 1 and NS becomes 2 in case of double shear. Whereas what is ANB? ANB is the net area we should calculate. Net area we are going to take as a 0.78 times of the grass area. Grass area is nothing but the shank portion area, nothing but ASP. What is ASP? ASP is the shank portion area of the board. That is, if you know the diameter, we can calculate the cross section area of the board. That is a circular one, pi d square by 4. Okay. So if you take 0.78 times of the pi d square by 4, then you will going to get A and B. So since in a thread portion, since we removed some material, we need to we need to end up with the lesser area. So this is what your the this what the formula for the nominal shear capacity of the board. So again, we should calculate parallelly the bearing capacity of the board. Sometimes the board will going to fail due to excess of bearing failure or the bearing force. So the design bearing strength of the bolts of the plate in a bolt in any plate we can calculate by using this formula. Okay, so VDPB equal to VNPB by gamma MB, where gamma MB is the partiality factor for material. Again, that is 1.25. In case of field fabrication or in case of shop fabrication, we could take always gamma MB as 1.5. Okay. Okay, next, if you go for VNPB, that is what is VNPB here? The nominal bearing strength of the bolt, nothing but 2.5 times of KB dt into FU, where KB is the factor we should calculate according to this, the pitches and edge distances, E by 3D naught, where 3D naught is the size of the hole, so, diameter plus the diameter plus the clearance, and pitch is the minimum pitch value, edge distance value, Fu is the ultimate strength, FUB is the ultimate strength of the board, Fu is the ultimate strength of the plate, and 1.0. Out of this, whichever is least, we should take that one as a KB value, where D is the diameter of the board, thickness is the thickness of the thinner plate, and Fu is the ultimate strength of the material. So material is nothing but plate. So this is what the two strength we should calculate while calculating the capacity of the single board. Okay. So in the next session, we're going to discuss the problems on the bolted joints. Thank you.